We should remember that the full scope of applications of scientific discoveries is rarely apparent at first, yet scientific advances can surreptitiously change our world as well as our worldview. If applied well, they can yield tremendous benefits, even many insights rooted in abstract theory, basic research that no one initially thought would ever have practical applications, has had a profound impact on our world. Genetic studies, which today aim to treat cancer, are rooted in DNA research that initially was focused on purely theoretical questions. Medical tools such as MRIs grew out of our understanding of the atomic nucleus. Nuclear energy, which has been used for good and ill, emerged from knowledge of the structure of the atom. The electronics revolution grew out of transistor development, which developed from quantum physics. The Internet was a byproduct of the computer scientist Tim Berners-Lee's work at CERN, the particle physics accelerator center that now hosts the Large Hadron Collider, to improve communication and coordination among scientists in different nations. GPS systems, ubiquitous today, incorporate Einstein's theory of relativity. No one even knew electricity would be important when it was first discovered, yet it is crucial to our current way of life. When first starting his studies, the geologist Walter Alvarez, whose father was a Nobel Prize-winning physicist, thought geology was routine compared to physics. Geologists were reconstructing relatively prosaic river and land patterns, while 20th century physicists were radically changing the way people thought about the world and how it works. But as plate tectonics, stratigraphy, and geological evolution became better understood, oil reserves and mineralogical deposits were discovered and exploited. What started off as idle curiosity developed into tools for searching for oil and minerals. The transition began in the 18th century, but geology escalated in importance in the 20th. Geology provided great dividends to our world. It literally fueled the modern industrial complex, and with it our economy and lifestyles, but many of our current environmental troubles too. However, as the legacy of Alvarez and others demonstrates, not just industrial applications, but basic research goals as well, have fueled important advances in our understanding of geology, connecting the meteoroid and the solar system to a wider context, the structure of the galaxy, seems like the right progression in this expanding intellectual adventure of grasping the connections between our world and the surrounding universe. I like to think of the research this book describes as a continuation of the appreciation of other sciences that Alvarez's work precipitated with its intertwining of geology, chemistry, and physics. That dark matter might complete the set of known relationships reinforces this continuity. Not only can we use geology to understand a cosmic event, but maybe with a detailed understanding of the nature of dark matter, will we come to understand the dynamics that threw a comet into our path in the first place. Though most people's interest in meteoroids, astronomers, and asteroid mining investors aside, derives from their potential consequences from life, the imminent danger presented by these flying objects is fairly minimal. Asteroids and comets are mostly in stable orbits, and those that do deviate to hit the Earth are usually pretty small. Only rarely do big objects digress enough to leave the solar system or strike the Earth. Based on the information I've presented, I hope you now have a better sense of what extraterrestrial bodies could hit in the future and how dangerous their impact is likely to be. This book has explained the multiple threads of evidence establishing the one solid example of such a connection, which is the KPG extinction 66 million years in the past. In some global sense, we are all descendants of Chicxulub. It's a part of our history that we should want to understand. If true, the additional wrinkle presented in this book would mean that not only was dark matter responsible for irrevocably changing our world, but also that some of it played a crucial role in allowing for our existence. In this scenario, from the dinosaurs' perspective, dark matter was evil after all, and the name scientists gave it was apt. But from a human perspective, this newly proposed type of dark matter was the instigator of one of the central accidents that changed the course of the Earth's development to the point where you could be sitting here reading this book. In Dark Matter and the Dinosaurs, I've tried to give a taste of the nature of scientific investigations, how we pin down what we know and advance beyond to uncharted realms. On the other hand, the history of the universe and of the Earth takes us on an exciting but challenging voyage into our past. If you think family history is difficult to trace, even when people are still around to tell the tale, think of the obstacles to extricating a past preserved only in inanimate rocks, many of which have eroded over time or been subducted back into the mantle below, or the complexity of understanding how dark substances, which we can't even see, created structure. Yet progress in science has revealed some of the remarkably intricate connections between the most fundamental matter's physical makeup and the features of the world that we see. Particles of dark matter collapsed to form galaxies. Heavy elements created inside stars have been absorbed into life. The energy released by decays of radioactive nuclei deep inside the mantle have driven the movements of the Earth's crust that have created mountains. I find our ability to make progress in understanding these deeper connections in the universe truly inspiring. Every time scientists have explored the boundaries of the known world, unanticipated discoveries have emerged.